So here now we'll talk about work done by gravity or against gravity. And we've done this last year a lot. Okay, this is your classic MGH calculation for gravitational potential energy. But in IB physics, we just need to remind ourselves how exactly it works. So gravitational potential energy, it would be the energy stored in an object as work was done on it to change its position vertically or away from another object in mass. And the objectives in this little video is to get you to practice calculating gravitational potential energy and then applying your basic conservation of energy rules involving gravitational potential energy. So the first question I have is, does gravity actually perform work? It's kind of strange. Gravity is a force that exists between two objects of mass. And later on, by the end of this unit, we're going to review a formula that I gave you for Newton's universal law of gravitation that looks like this, where if I have an object 1 of mass and another object of mass, and I separate them by a distance, I can calculate the force of gravity that exists between them. But gravity doesn't go out and perform work on objects. Work is usually done against gravity. This person here had to walk up these stairs. So this person is lifting himself up and moving in a gravitational field and having to do work separating him from the surface of the earth. So the work done is actually by a person against gravity. Okay, and the work would be the force of gravity times the distance that he moves. Now, if this distance is relatively small, let's say on the order of like 10 meters, okay, it's pretty simple to calculate the gravitational potential energy. But if we're talking that that distance moved is kilometers, or I'm climbing a mountain, the work is not as simple as I'm going to present in this video. We'll get back to it when we look at this actual formula for force. That I would have to plug in here. But what we do know is to calculate the force of gravity on close to the surface of the earth, we can just say that the force of gravity is actually equal to mg, if you remember, where g is equal to 9.81 meters per second squared. Let's just assume that we're talking about small changes in distance. Then the acceleration of gravity is 9.81. This is a very simple thing to calculate. So the work performed by this dude climbing the stairs is going to be equal to m times g times I'm going to call it the height, the vertical height that he moved, which is going to be equal to, let's say he's 100 kilograms. That's his mass. The gravity is 9.81 meters per second squared. And the height, let's say, is 10 meters. Okay, that should be equal to the actual work that he would do measured in joules. Okay, so 1,000 times 9.81, we're talking 9,810 joules. Okay, that's how much work you would have to do. Not bad, not bad. I'm sure you burned a couple calories over there. All right, and we did these last years in projects. Okay, you definitely knew how to calculate the work done against gravity at small distances. But you can see it would get a little complicated if we go much higher distances. G is no longer 9.81, it becomes something different. So at the end of this unit, we'll come back and learn how to factor that in. All right, so that would be work performed against gravity. And now this person up here has gravitational potential energy that we can calculate, mgh. So what can we do with it? Well, the work performed by and against gravity is independent of the path that it followed. It depends only the vertical distance separating the initial and final positions. Okay, so if this person climbed straight up with a rope, he would have to do the same amount of work as if he actually just took a longer path. Now, how does that work out? Well, the work that this person's going to be doing climbing the stairs, it's like a ramp, would be like mg sine theta times d, which is the distance of the ramp. Or he can take the shortest route possible, and that would be mgh. If I would plug these numbers in, that distance, this angle, mg, I would end up having the exact same calculation as if he did this. So another way of looking at ramps, and if I want to calculate the work to get up a ramp, rather than doing this complicated side, I could just look at the total vertical height that person climbed, okay, h, and multiply by mg, and I would immediately calculate the work I'd have to do to climb up that ramp. That's kind of cool. Another thing that this statement is saying is, let's say I am here, okay, and I go, okay, despite the fact that I went above my position, which will be like, you'd have to, wow, that would be really hard. No, that wouldn't happen in real life. I would never be able to get above that position. And I want you guys to think about why that was wrong. Okay, but if I'm a marble and I go down this ramp, okay, I have gravitational potential energy. Okay, now the total amount of energy, when I get over here, the total amount of energy that will be converted into, let's say, kinetic energy, will be the same as if I just fell straight down. It doesn't matter the path, okay? Assuming there's no friction on that ramp. And that's what the statement is saying, is that there's many ways to get there, but they would all be the same. It's just the vertical distance times gravity times your mass would tell you the total gravitational potential energy. Doesn't matter your path to get there, all right? So how do I apply my understanding of gravitational potential energy in conservation of energy? Well, most often the case is that your gravitational potential energy is usually converted into kinetic energy, which might be converted into work against friction and heat. Okay, these are types of conservation problems that you would end up doing. Now, in a classic problem that you'd always get when you're learning conservation of energy and gravitational potential energy is the roller coaster problem. That's where you have a roller coaster with a bunch of mass on it, and it's going down a ramp that has a vertical height of 25 meters, comes back up and ends 20 meters high. And problems that I can ask, or that anybody can ask, is, well, what would your velocity be at this point on the roller coaster? And what would your velocity be at the finish, assuming that there's no friction? Okay, well, in order to calculate that, I need to know my changes in vertical distance. And the problem doesn't tell me anything about the mass. That's kind of strange. I guess mass is not important. Let's see why. Okay, so I'm going to just analyze this part because that would tell me what I need to calculate velocity. All right, so let's plug these formulas in. For gravitational potential energy is going to be mgh. Okay, the mass of the roller coasters, well, I guess I need it, but it's not there. G is acceleration of gravity, and h is my change in vertical height. Okay, is going to be equal to 1/2 mv squared. Oh, I'm starting to see. So v is my velocity at that point. That's all that energy converted to kinetics. That'd be my velocity at that point. M was the mass of this roller coaster at that point, and 1/2 is there. So why in the problem did they not tell me the mass? Well, it just happens that your masses will cancel out. And then, if I rearrange to solve for the velocity, 2gh square root is equal to my velocity. You can try to do the algebra to see why that's the case. Okay, which is pretty interesting because we've seen something like this before in a kinematics equation. When you look at the v squared is equal to u squared plus 2as, okay, and if my initial velocity is 0, then v squared is equal to 2as, and then v is equal to the square root of 2as. That's interesting because kinematics told us that this equation exists. Okay, this velocity at any point is going to be equal to 2 times the acceleration, which is gravity in this case, times my displacement, which was 25 meters. Okay, this formula is that formula. And we came to the same end formula using two different theories. This is using kinematics equations and acceleration, and this is using conservation of energy. That's kind of how physics can prove things are true, by looking at a principle and coming at it using different theories and angles. If they give you the same result in the end, it's more likely that those theories are true. That's a big TOK link, okay, for how knowledge is acquired in mathematical thinking. Okay, how do we validate models to say that, yeah, this is likely a true model? Okay, if it gives us the same result using a different model, then it's likely true in nature. Okay, so you might want to talk about that in an essay. All right, so that's cool. All right, so to calculate the velocity of this roller coaster at that 25-meter change in height, I would just plug the variables in. So my velocity is going to be equal to the square root of 2 times 9.81 meters per second squared times 25 meters. okay? And I don't have a calculator on me right now, but that would give me the velocity over there, okay? Which is gonna be faster than the velocity here because the change of height is only 20 meters. So it would go really fast, and then I'm going from kinetic energy up a little bit. I have to do some work against gravity. So I lose some of that kinetic energy, and I'll be left with my final velocity, which I can calculate as mgh, except with my h being 20 meters. So instead of 25, I'll put 20, and then I can calculate my velocity. All right, so just remember this setup. mgh is equal to 1/2 mv squared is a great conservation of energy example to calculate the velocity of an object when it's dropping. All right, and that's essentially it for gravitational potential energy, but I'll come back when we talk about gravity. All right, and we'll see that this system only applies when your distances are not that huge, like 100 meters or so. Anything more than that, it doesn't work out anymore.